So continuing into our study on gas laws, we get to ideal gas law. Now, ideal gas law, in a nutshell, in its simplest form, is the combination of your simple gas laws. So the combination of simple gas laws. Not the best definition, but if you just need the basic understanding of what it is, then there you go. It's the combination of your simple gas laws like Boyle's law, Charles' law, Avogadro's law. Now your ideal gases, they are going to be a theoretical gas. They are a theoretical gas. Your ideal gas or your perfect gas is going to be to help us understand the relationship between our four gas variables. Those variables are pressure, volume, moles, and temperature. So an ideal gas is a theoretical gas to help us understand the relationship between our variables, which are pressure, volume, moles, which is the amount, and temperature. Now, ideal gas follows a couple of different traits. The particles of the gas are extremely small and they don't occupy any spaces. That means an ideal gas does not take up a volume. But we know gases do in fact take up volume. They have a mass, they take up volume. But under ideal gas, we consider it to not take up any space. So an ideal gas does not occupy space. Which is to say, volume. Second trait is an ideal gas has constant straight line motion. It's constant straight line motion. And the third one is there's not going to be any interaction or any forces between your gas particles. The only thing that happens is particles collide with the wall of the container or with other gas molecules themselves. They have no force interactions, no attraction, no repulsion, just collisions. So no force interactions. Now we do know all these things do happen with real gases. So real gases, they have volume, so they do indeed take up space, have attractive forces, and as a result of that, the volume of a real gas is larger than an ideal gas, but the pressure of a real gas is lower than that of an ideal gas. But your real gases do act like ideal gases at low pressure and high temperatures. So with volume, real gases, our volume is bigger than ideal gases. But with pressure, a real gas will be lower than an ideal gas. And the last thing to keep in mind is real gases act like ideal gases at low pressure and high temperature. So these ideas help us to understand how the relationship between pressure, volume, moles, and temperature actually work if we consider gases to be ideal gases. Now, since ideal gas law is a combination of all your basic gas laws, that means there is a formula since it's a relationship. And that formula is PV equals nRT, or as I heard it referred to as perv nert. So PV equals nRT, P is pressure, V is volume, N is moles, T is temperature. All four of those you're familiar with, or you should be. The only new one is R. R is the universal gas constant. Universal gas constant. There are two values for this R constant. If your pressure is measured in ATM, your number is 0.0821. If your pressure is measured in kilopascals, it's 8.315. Make sure you make note of your formula and those two gas constants. Those are super important. Now the best way to learn how to use ideal gas law or perv nert is just practice problems. Let's do that. So we're going to calculate the volume which 1 mole of gas occupies STP. So we have 1 mole of a gas, 1 mole of an ideal gas, and it's at standard temperature and pressure. So you could say we have a standard gas at standard temperature and standard pressure, and we're going to solve for what its volume is. So if all your conditions are standard, then when we find this volume, we could consider it standard volume of a standard ideal gas at standard conditions. And that number will come into play later on. But for right now, let's just work out this problem. First thing I need to do is pick out my given information. So I'm calculating volume. So I'm looking for V, which 1 mole of a gas, so that's N, is 1 mole, occupies at STP. Standard temperature is 0 degrees Celsius, but my gas laws have to be in Kelvin, so that's 273 Kelvin. Standard pressure is 1 atmosphere. And I see I have all 4 gas variables, so I also need to include R. Well, what's R? Well, I'm dealing with ATM, atmospheres. So this is going to be 0.0821. So it looks like we're dealing with ideal gas law. So let's identify our formula. Ideal gas law is perv nert, or PV equals nRT. Now we just plug in. P is 1. V is volume, that's X, that's what I'm looking for. N is moles, that's 1 mole. R is my gas constant, 0.0821. T is temperature, and that's going to be 273. Now we can just do a little bit of algebra. So 1 times X is 1X, set equal to 1 times 0.0821 times 273. We get 22.41. I divide by the value with X. 1 cancels out. X equals 22.41. I need a unit. Since I'm looking for volume, that's going to be in liters. So our answer is 22.4. You'll see that number later down the road as standard volume of an ideal gas. So if you got 1 mole of a gas at standard conditions, it's going to take up 22.4 liters. That value will come into play with gas stoichiometry later on. I would make a little note of it somewhere. Alright, let's do another one. Oxygen gas is collected at a pressure of 5 atmospheres in a container which has a volume of 3.2 liters. What temperature must be maintained on 0.5 moles of this gas in order to maintain this pressure? Alright, let's pick out our information. So we have a pressure of 5 atmospheres. I got a volume of 3.2 liters. what temperature must be maintained. So I'm looking for temperature on 0.5 moles. So I got mole amount 5.5 in order to maintain that pressure. So I got my four gas variables. So I need an R constant. I'm dealing with atmospheres, so that's 0.0821. So I know I'm doing ideal gas law. I know I'm using my Perv-Nernst formula. So let's just plug in and solve it out. So P is 5, V is 3.2, N is 0.5, R is 0.0821, and temperature is what I'm looking for. Now I just solve it out. 5 times 3.2, and I get 16.5 times 0.0821 is 0.0411 x. So divide by the value with x, that cancels out. 16 divided by 0.0411, x is 389.77. Since I'm looking for temperature, this will be in kelvins. If the question had specified what is this temperature in Celsius, that's an easy change too. Just subtract 273, and then you would have your temperature also in Celsius, and that'd be 116.77 degrees Celsius. But either way, there is our answer. And let's do the one last one. What is the volume of a balloon if it contains 3.2 moles of helium at a temperature of 30 degrees Celsius and standard temperature? So let's pick at our given information first. What is the volume? So I'm looking for a volume. If it contains 3.2 moles, so I got moles at 3.2 of helium at a temperature of 30 degrees. So a temperature of 30 degrees Celsius. This needs to be Kelvin, so I add 273 and I get 303 Kelvin. And standard pressure. So pressure is 1 atmosphere. So our constant, since we're doing ATM, is 0.0821. So we're using ideal gas law or Perv-Nernst. So PV equals nRT. Pressure is 1. Volume is what I'm looking for. That's X. N is 3.2. R is 0.0821. And temperature is 303. Now let's just solve it out. 1 times X is 1X. 3.2 times 0.0821 times 303. And I get 79.6. Divide by the value with X. 1 cancels out. Divide by 1. X equals 79.6. But 79.6 what? I'm dealing with volume. So this is liters. There is my answer. So all in all, ideal gas law isn't too bad. It's just using the formula. Pick out your variables. You know which variable is which by the unit of measure. Once you got those listed out, write your formula and plug those variables into the formula. Do a little bit of algebra and you're there. But as I said earlier, this lesson is an important one, so make sure you understand how to use your formula, how to calculate it, because it will reappear in other lessons as we go through chemistry and physics. But I hope this video helps, and as always, good luck on your tests.